This video, we're going to look at the first example of shear force diagrams and bending moment diagrams from the course notes, which you'll find on page 14. The example presents us with a beam which has a load applied at point C and is supported at points A and B, and all the forces in the diagram are labelled and as the distances at which force C is applied from each end. So the first thing we're going to want to do is to create our shear force diagram. Now, to make things a little bit easier here, I'm just going to draw a straight line as our baseline for our shear force diagram. So this represents the beam and the forces applied to it. And either end, we'll just mark that if it's on the line itself, we're saying this is zero forces applied, and we'll mark all our forces relative to this line. So what happens then? First, we can look at the shear force at A, and this is given in the question as 3.33 kilonewtons. So it's a force acting vertically in the positive direction. So what we would do in this case is we draw a line acting up from the left-hand side of the beam, and we give that a length which should be equivalent to 3.33. We attempt to draw all of our lines, a proper diagram, we will draw all of our lines so that they're proportionate in size. So a force of 2 would be twice as long a line as a force of 1 kilonewton. So we'll draw a line here and we'll call this 3.33, and I'm not going to use a ruler for all I should be using the ruler. I'll try not to. I won't use the ruler for all of this. We've got a line coming up from 0, and that's taking us up to 3.33 kilonewtons in the positive direction. Now, what happens is our next force moving left to right is a 5 kilonewton force acting down the way in the beam. And so on a diagram like this, where we have what are called point forces applied, so they are acting at individual points, there's no UDL involved here, we'll have a straight line, there'll be no change in our shear force until we get to the next load that's applied. So we're going to mark along here as if we're going 2 meters along the beam, so that's about this far along, and then we're told that a 5 kilonewton force has been applied beneath the acting down the way. So we're at 3.33 and we've got to go down 5. Well, what we see, the shear force at C is going to be, I'll put C here, C, going to be 3.33 where we started from, minus 5, and that's equal to 1.67 kilonewtons. So we'll go down 3.33 and we'll continue to go down to 1.67, so we're minus 1.67 here, because that's the effect of starting from 3.33 and travelling down 5 kilonewtons, the force that's being applied at point C. And as I said, when we are working with individual forces, there'll be no change in the shear force between points at which force is applied. And so the next force is applied at the end of the beam. So if we go along all the way to our right-hand side here, which is point B on our beam, we can see from our diagram a force of 1.67 kilonewtons has been applied in the upward direction. And of course, we're at minus 1.67, we're going 1.67 in a positive direction, and that's going to take us back up to 0. And that's what we would expect to happen in a scenario in which we have a balanced beam, that the supports at either end are going to be counterbalancing the downward load and leaving us with a shear force of 0 where the supports are. So that's how we do a shear force diagram for a beam which we have individual loads. Now let's have a look then at the bending moment diagram for this. So I'm just going to, for reference, I'll copy the shear force diagram, the slightly neater one that they have on the course notes. I'll rub mine out now that we've seen it, and I'll copy the one from the course notes so we can have that for reference when we work in the bending moment diagram. So that's a version of the diagram I just produced there, but with nice neat lines. As you can see, we got 3.33 down 5, which takes us to 1.67, and then back up 1.67 at the end. So that's our shear force diagram.